So in this video, I'm going to continue on with this idea about the graphical method, but instead of thinking of this problem as a linear program, I'm going to take it as an integer program. So just to refresh everybody, we have this Lego workshop here. We have a set of an objective function, 3 constraints, and then non-negativity. And we had 3 different steps for the graphical method. We had this graph each constraint at equality. We want to identify the feasible region and then graph the isoprofit line and essentially push it until it just intersects with the feasible region. These same steps apply for an integer program, but a main difference is going to be what's the feasible region for an integer program versus a linear program. And so just to remind everybody, this is what the feasible region looked like. It was here in the bright green, where all of these points, any point in here, would satisfy all of our constraints, and we graphed each of our orange isoprofit lines and pushed it out until it intersected with this optimal point 2, 6. And so when we place an integer restriction on the variables, we're further constraining the problem. So the best we could do, possibly, is the objective function value of the optimal linear program, but it could be in some cases where you can't even attain that because your solution is not integral. And so here we're going to work through our model for a linear program. So first I'm just going to write out that model, the Lego Workshop model, as an integer program. So here we have our integer program. And so we're going to again say maximize 3x1 plus 2x2, subject to 2x1 plus x2 less than or equal to 10. The constraints here are exactly the same as in the previous model. The only thing comes is when we define our variables. So here we're going to say that x1 and x2, now instead of being greater than or equal to 0, we're going to say that they belong to the set of 0. This is union, so it's 0 and or here, any of these values, z plus. So z is our set of integers. When I add on this plus here, I get the positive integer. So what this is saying is x1 and x2 can take on any value, okay, there we go, any value 0 or a positive integer there. And so our steps apply from before, and so we're going to graph it just like we did before. So I'm going to define my axes. So here I'm going to label this as x1, and this is x2, and we know we have to be greater than or equal to x1 and x2. We're going to continue to graph all of our lines at equality, so I'm going to keep with the same colors, and so I'm going to graph 2x1 plus x2 equal to 10. Again, this is going to cross at x1 equal to 5, which is this here, and x2 equal to 10, which is this right here. Okay? And so I'm going to draw the line through this. And this here is going to be 2x1 plus x2 equal to 10. There. I'm going to do the same for our other constraints. So we went to green next. And we're going to do x1 plus x2 is equal to 8. So this crosses at 8 for both of them. So that's going to be this here and this here. Okay. So this is going to be x1 plus x2 is equal to 8. Then I think I switched to purple, and we have our last constraint that x1 is less than or equal to 4. So I'm going to graph that at equality as x1 is equal to 4. And we can think when we're identifying our feasible region, we can again do these directions like we had before, where we were in those directions. And before we highlighted everything in this feasible region here in green like that as our feasible region. But not all of those points satisfy this here of our integer restriction. Instead, only the points that are integral satisfy those restrictions. So our feasible region here is a disjoint set of points, of discrete points. 0, 0 is feasible, 0, 1, 1, 0 is feasible, so on and so forth. All of these points here that are integers is our feasible set. So instead of it being the full region, it's these points. And so when you have two variables like we have, you can again do the same idea of the isoprofit line. But now instead of pushing it out until it doesn't intersect with you are pushing it out until it doesn't intersect with a feasible region, but you're essentially pushing it out until it just intersects with that last point of the feasible region. So we're going to graph it like we did before. So it's going to cross here at 2 and 3. And so I'm going to graph that again. So you're going to cross here, and here. And the same idea applies where you push it out, we're parallel with this line, or approximately parallel, that's a little off there, and you keep pushing it out, and only the points that intersect with it, so like you see that here it's intersecting with that point, are the feasible points along that line. Not every single point along this line is feasible. And so in this example, we end up where our optimal solution to the LP is feasible to the IP. But that isn't always the case. You can think that maybe if we just tweaked these constraints, that this point here would not be integral. So maybe it was like 2.2 and 6.1, in which case that would not be feasible to our integer program, and you would end up with a different solution. But this is just a special case or a special linear program that ends up where its optimal solution is feasible to the integer program. So here again we end up with x is equal to 2, 6 as our optimal solution, and z star is equal to 18 once you plug in those values into the objective function there. And so in this case here, our LP optimal solution is equal to our IP optimal solution. This is not it will not always happen. Okay, so just to review, we've gone over graphical method. Same general steps apply for a linear program as well as an integer program. And we've shown what a feasible region looks like for a linear program as well as for an integer program and the slight differences between the two there.